Your turn, problem 2. Consider the following equilibrium reaction. It's the same same reaction as we did in problem 1. The H2 plus I2 yielding 2HI. In this one, though, we're going to introduce 0.40 moles each of H2 and I2 into a 1 liter evacuated flask. Remember that evacuated means that there is no other gas present. It's essentially a vacuum in the flask until you add in the H2 and the I2. It's allowed to come to equilibrium at 425 Kelvin, and the Kc value for this is 54. So we want to calculate the equilibrium concentrations for the reactants and the product. And then after we do that, we want to calculate the partial pressures of each of the gases present. And there's a little hint here: when you go to calculate the partial pressures, you'll want to use the ideal gas law. So welcome back. Let's take a look. First thing you wanted to do here was to set up an ice chart. And because the volume of the flask was 1 liter, we want to go ahead and calculate the concentrations, and it's really nice when it's 1 liter because you just divide the moles by 1 and you get the initial concentrations of the H2 and I2, which are both then 0.4 moles per liter. Now, the change in the concentrations of H2 and I2, because the stoichiometric coefficient is 1 for each of those, would just be minus x. Because there's a stoichiometric coefficient of 2 with the hydrogen iodide, for every amount x that H2 and I2 change, the HI concentration will change by 2x. So that change is reflected in the ice chart. And then finally at equilibrium, we would have 0.4 minus x moles per liter for each of the H2 and I2 reactants, and then 2 times whatever that value for x is will be the molar concentration of HI. So we go ahead and write the equilibrium constant expression. So 54 is equal to the concentration of hydrogen iodide squared divided by the product of the concentrations of H2 times the concentration of I2. When we substitute in the equilibrium concentrations from the ice chart, it would be 2x squared, and I should say the quantity 2x squared divided by 0.4 minus x times 0.4 minus x, and we can simplify that to 4x squared divided by 0.4 minus x, that quantity squared. After substituting in the equilibrium concentrations with the x values, you'll notice that this is a perfect square. And this is an ideal situation for us because what it allows us to do is take the square root of everything in order to simplify this. So we would have the square root of 54 is equal to the square root of 4x squared divided by the square root of the quantity 0.4 minus x squared. After I square root each of the quantities, I get 7.3 is equal to 2x divided by 0.40 minus x, and I can work from there to solve for x without having to use a quadratic equation, which is a real advantage in terms of time and simplicity of calculations. So using algebra, I multiply 0.40 minus x by both sides of the equation, which cancels it from the right side and leaves me with 7.3 times that quantity, 0.40 minus x, is equal to 2x. I multiply through the quantity 7.3 times the quantity of 0.40 minus x equal to 2x. So I get 2.9 minus 7.3x is equal to 2x. And then I just add 7.3x to both sides of the equation so that I can cancel it out of the left side, and it would leave me with 2.9 is equal to 2x plus 7.3x, and that would be equal to 9.3x. And that on this, you'll notice that I forgot to put the x on the 7.3. Would you go ahead and correct that on your paper so that you make sure that the 7.3x does show up there? And I would appreciate that as you work through this. Now, continuing on, again, will you please put an X with the 7.3 in that top algebraic expression? 2.9 is equal to 2x plus 7.3x, which would equal 9.3x. We're going to divide both sides of the equation by 9.3 so that we can isolate x and solve for the value of x, which would be in moles per liter. So 2.9 divided by 9.3 is equal to x, which would equal 0.31 moles per liter. We go back up into the ice chart and we subtract 0.31 moles per liter from each of the beginning concentrations of H2 and I2, so we are left at equilibrium with 0.090 moles per liter each of hydrogen and iodine gases. And for the concentration of HI, we would multiply 2 times the value of x, which is 0.31 moles per liter. So the equilibrium concentration of hydrogen iodide will be 0.62 moles per liter. What remains for us to do with this problem then is to find the partial pressures of each of the gases involved here. So in order to do that, we're going to use the ideal gas law, and the ideal gas law is PV is equal to nRT, where P represents pressure, V represents volume. In this case, we're going to use liters. R will be our universal gas constant, 0.082 liters times atmospheres per mole times Kelvin. T is the temperature in Kelvin. And in order to do this, I'm going to go ahead to simplify these by just converting back from my moles per liter concentration to the number of moles of each gas. And you'll remember from stoichiometry that if we take the volume in liters times the moles per liter concentration, the liters will cancel and we'll be left with the number of moles of gas. So we do that each. It's really nice here because the volume of the flask is 1 liter, so it's just 1 liter for the hydrogen iodine times 0.090 moles per liter, which gives us 0.090 moles each of hydrogen and iodine, and then 1 liter times 0.62 moles per liter of hydrogen iodide gives us 0.62 moles of hydrogen iodide. Because the number of moles of hydrogen equals the number of moles of iodine gas present, we can solve for both of those, because if the moles are equal, then the pressure exerted by that quantity of gas will be equal. So pressure will be equal to nRT divided by V. So we plug in our numbers, 0.090 moles times 0.082 liters times atmospheres over a mole times Kelvin times 425 Kelvin. Gives us a partial pressure for the hydrogen and iodine of 3.1 atmospheres. For the hydrogen iodide, that pressure will be equal to, again, nRT over V, so we'll take our 0.62 moles times 0.082 liters times atmospheres per mole times Kelvin times 425 Kelvin divided by the 1 liter, gives us a partial pressure of hydrogen iodide of 22 atmospheres. So we now have our pressures of each gas at equilibrium, 3.1 atmospheres of hydrogen, 3.1 atmospheres of iodine, and 22 atmospheres of hydrogen iodide. We can use Dalton's law then that the pressure total will equal the sum of the partial pressures of each gas in the system. So our pressure total here would be 3.1 atmospheres of hydrogen plus 3.1 atmospheres of iodine plus 22 atmospheres of hydrogen iodide, which would equal 28.2 atmospheres total in this flask, total pressure. This is the end of the video podcast series, part 1-7 of Equilibrium here at Ontario High School. I want to leave you with another quote from Mark Halperin. "If it weren't for music, I would think that love is mortal." Isn't that grand? Now, there's still 1 or 2 more parts. We'll see how it goes, so stay tuned for those and engage.